Okay, so we're going to continue with the classification of principal G bundles on the N sphere. Now, at the end of last time, I went through the argument for n equals 1 and G is equal to a discrete group. And I won't repeat that argument because the general argument is going to be very similar, and I'm going to do it in just a moment. But first, let me remind you what the answer was. The answer was that isomorphism classes were in one-to-one correspondence with conjugacy classes of pi naught of G. In other words, pi naught of G divided by pi naught of G, where when I divide, I act by the conjugation action.
And this is also true for continuous.
Pardon?
This is also true for continuous group.
And that's what I was just about to say, right. So, exactly. So, this is also true for any G bundle on S1. By a small modification of the argument I gave last time, and there's a paragraph in the notes where I spell out the details. Speaking of notes, nobody seems to be in today. So I can't give you a Xerox of today's notes. I imagine that by next time we'll have a set of notes for you. Sorry about that. Okay. So now let's graduate to n greater than 1. And to start with, let's take G connected. So pi naught of G is the zero group. Trivial group with one element. Okay, so the argument, as I said, is very similar to what we discussed before. So we take our n sphere, and we take two patches, which we could call the north hemisphere and the southern hemisphere. And we can have these overlap in some band around the equator. Equator being a copy of Sn minus 1, because the whole thing is Sn. And for topological purposes, the fact that this band, this overlap, contracts to Sn minus 1 means that I might as well just think of the transition map G plus minus, which goes from D plus n intersect D minus n to G. This is equivalent topologically to G plus minus, which goes from the n minus 1 sphere to G. There's clearly not going to be any interesting topology in the variation in that direction. Okay. So when we have a bundle built by this construction, this is called the clutching construction. Then when we have such a bundle, then we automatically get a certain homotopy class. So G plus minus has a homotopy class. Okay. So let me be a little more precise about that. So since we're assuming that n is bigger than 1, Sn minus 1 is connected. So we can choose a base point, theta naught, in Sn minus 1. And without loss of generality, because we can, of course, change our trivializations, as we're going to start doing systematically, we can assume that g plus minus of theta naught is just the identity. So then our transition function defines a homotopy class in Sn minus 1 theta naught, mapping into G, the identity. Plus minus is such a homotopy class. Okay, now let's remember, though, that we can always change our local trivialization by L sub alpha, which goes from our patches U alpha into G, to take the old transition functions into the new transition functions, L beta inverse, G beta alpha, L alpha. So now I claim that two clutching maps define the same homotopy class if and only if the bundles are isomorphic. Okay. And so now let's check that claim. So let's suppose first that, so let's go this way first. So suppose that G plus minus 1 and G plus minus 2 define isomorphic bundles. So let's choose coordinates. Let's call them r plus minus and theta on these hemispheres, d plus minus n, so that the equator is at r plus equals 1, and the pole is at r plus equals 0 in d plus. And similarly, the equator is at r minus equals 1, and the south pole is at r minus equals 0 in the southern hemisphere. Of course, I'm using the words hemisphere, but this is true for all n, where n is bigger than 1. Okay. Now, since the bundles are equivalent, there exist continuous maps L plus from d plus n into G, and L minus from d minus into G, so that this transition function is related to this transition function by this rule here, change of local trivialization. So that means we have L plus inverse at r plus equals 1 and theta, L minus at r minus equals 1 and theta. Is there any question about that? On the other hand, these L plus and minuses extend continuously to the rest of the disk. Okay? So L plus is a nice continuous map all the way up here into G, and L minus is a nice continuous map down here into G. Okay, well, and look at the homotopy, L plus inverse of t and theta, g plus minus 2 theta, L minus of t and theta. Now that's a homotopy, f sub t of theta. So what do we recognize about that? Well, first of all, f sub 1 of theta is equal to g plus minus 1 of theta, obviously. It's continuous, and f sub 0 of theta is equal to L plus inverse, let's call it L plus naught inverse, G2 plus minus of theta, L minus naught. Now what have I done here? I've done something a little tricky. L plus 0 is equal to L plus of r plus equals 0, and theta is independent of theta, and in particular well-defined, because I'm choosing these polar coordinates. So you see, this isn't a function of theta, this is just some element of the group. So since we're assuming G is connected, we can homotope it to 1. And by the same token, we can also homotope this guy to 1. So therefore, f naught of theta is homotopic to g plus minus 2 of theta. And therefore, g1 is homotopic to g2. Is there any question about that? That should be crystal clear. Okay? So if I've got equivalent bundles, then the clutching map associated with those two equivalent bundles are homotopic maps. Anybody have a question? Okay. So what that does is that gives us a map from the isomorphism classes, let's call it principal G bundles on Xn, to the homotopy group, pi n minus 1 of G. It's a well-defined map. This is the isomorphism classes of principal G bundles on Xn. Now, clearly the map is onto. Why is the map onto? Why is the map onto?
This is pi sub n minus 1.
That's right. You see, what is this G plus minus? It's just the clutching map along the equator, which is an n minus 1 sphere. So a map of the n minus 1 sphere into G defines an element of pi n minus 1 of G, right? That's what the homotopy group is. Okay, so why is this map onto?
You can always reconstruct using transition maps.
Thank you. You take any element here, it's realized by some map from Sn minus 1 into G. That's the definition of pi n minus 1 of G. And you use that as the clutching map. So you make your bundle that way. Okay? So what do we have to show? We have to show the converse. We have to show that if G plus minus 1 is homotopic to G plus minus 2, then they define isomorphic bundles. Okay, so how do we do that? Well, if g plus minus 1 is homotopic to g plus minus 2, then g plus minus 2, 1, g plus minus 2 inverse is homotopic to 1. All right? So let's use that homotopy to define L plus. As we can say, L plus is going from d plus m to g. So then my change of transition functions, if I take g tilde plus minus equals L plus inverse of theta at r plus equals 1, and g plus minus, I guess I want 2, actually 1. And then I take L minus here, but I'll take L minus to be 1. Well, you see that this is equal to g plus minus 2. And yet, this is the homotopy to 1, so the L plus extends continuously to the northern hemisphere. And so is a valid change of trivialization. Okay. So that shows the converse. So then we have a theorem, we just proved, that if n is greater than 1 and g is connected, then the principal g bundles on an n-sphere is the same thing as a set as pi n minus 1 of g. Now let's see, people are awfully quiet. So maybe I'll give you another point of view on this. A variant of this argument says that if we had a global cross-section, then g plus minus would be homotopically trivial. Okay? Let's see why that's true. Well, to say that we have a global cross-section, there exists a global cross-section, means that there exist maps, let's call them g plus and minus, from d plus minus n to g, so that g plus at r plus equals 1 in theta is equal to g plus minus of theta, g minus at r minus 1 equals 1 and theta. That's what the existence of a global cross-section means. But then look what that says. We can bring this to the other side, so we have g plus of r plus equals 1 in theta times g minus of r minus equals 1 and theta inverse equals g plus minus of theta. Okay? And therefore, if we consider g plus of t and theta times g minus of t and theta inverse, this is a homotopy to the constant map. Right? Because at t equals 1, it's g plus minus of theta. And at t equals 0, these are just constants in theta. Okay? And that is the constant map. So that's a variant of this argument, not quite as complete. But this shows you that if you had a global cross-section, then your transition function is homotopically trivial. Okay. Now, let me give you some examples. So I discussed an example on S1 with a discrete group last time. So example 2 is to consider principal U1 bundles over the 2-sphere. Example 2, we can let principal U1 bundles over the 2-sphere is in one-to-one correspondence with pi 1 of U1. And what is pi 1 of U1? Z. Right, thank you. Okay, that means that for every integer, there is an inequivalent principal U1 bundle over S2. And now we looked at a particularly interesting principal U1 bundle over S2 last time, the Hopf vibration. And the Hopf vibration, you see, the Hopf vibration corresponds to the integer plus or minus 1, depending on how I orient things, which is a generator of Z as an abelian group. And the trivial vibration, S2 times S1 corresponds, or times U1, corresponds to which integer? Which integer? So in this correspondence between principal bundles and pi 1 of U1, which is Z, the trivial bundle corresponds to which integer? 0. Right. If we have the trivial bundle, we can take our clutching function to be the constant map. It's clearly in the zero homotopy class. Okie dokie. Now you see there are a bunch of other bundles here. Right? One for every integer. And if you take the notes and you actually do some of the exercises, you'll see that those are lens spaces. So you see you can take the up vibration, and remember that there was a free U1 action on this up vibration. So in this U1, we can take a subgroup which is isomorphic to Z to the N. So this subgroup here is isomorphic to, I said Z to the N, I meant Z sub N. Omega is e to the 2 pi I over N is a primitive nth root of unity. Thank you, Sal. And so now we can freely divide that. Now, if you think about it, a circle divided by Zn is still a circle. So this is still a principal U1 bundle over S2. And I'll let you think it through. This corresponds to the integer n. Under this correspondence. Okay, here's another example. So we're going to show in this lecture, or no, more like next lecture, that if I look at the group of projective special unitary transformations, which means I take U1, Un, and I divide by U1, I can do that. You see, U1 is a central subgroup. So if I divide Un by U1, I still get a group, because U1 is in the center. Now, in my group theory course, I always show people that that's the same as SUN mod Zn. I'm sure you can work that out. Where this Zn here is the center of SUN. Everybody know that? Right? So the Zn here, what is the center of SUN? The center of SUN they have to be proportional to the unit matrix. They have to be n by n, and they have to have determinant 1, so they look like this. Okay, so that's the center of SUN is, again, a copy of Zn. And so we have this quotient here. And so now if we take principal PSUN bundles on a 2-sphere, that is pi 1 of SUN mod Zn. And we're going to show that that's equal to Zn. So here we had infinitely many distinct principal U1 bundles over the 2-sphere. Here there are only n distinct principal U1 bundles over the 2-sphere. And last example. Let's talk about SU2 bundles over S4. So if we consider principal SU2 bundles over S4, then by the theorem we just proved, that's in 1-1 correspondence with pi 3 of SU2. And what's pi 3 of SU2? Z. Good. So, again, a lecture or two ago, we constructed a particular SU2 bundle over S4. You might remember the vibration of a sphere by a sphere. And we're going to study this in more detail later. This, again, corresponds to a generator of this Z. And again, there's infinitely many distinct bundles. These are all related to instantons. And this integer here is related to the instanton number. Whereas for these principal U1 bundles over the sphere, these are related to monopoles. And this integer here is the monopole number. I'll be explaining more about that later. Now, one little loose end to tie up here. If pi naught of g is not 0, how does this theorem change? Well, you can think through the argument here. I encourage you to do it. And what you'll realize is that it doesn't change very much. It just changes by the action of pi naught of g on pi n minus 1 of g. You see, if you have an element of pi naught of g, you can take any element in any component you like. Say take some g tilde, which is not connected to the identity, and you have some map here, g plus minus of theta, and you can change that to g tilde inverse g plus minus of theta, g naught tilde. And you see this will still satisfy the property that theta naught is equal to 1. Okay. But it might, in general, it will give you a different transition function. So pi naught of g acts on pi n minus 1 of g, and the general theorem is that principal g bundles on Sn are in 1-1 correspondence with the orbits of this action on pi n minus 1 of g. All right. Now, are there any questions about that?
So if there's a group structure on this pi.
There is not a group structure here.
No, okay, if G is the same connected, if G is connected, so you don't have to.
Oh, sorry. Wait, a group structure where?
Oh, pi n minus 1 G. So I'm asking.
Oh, well, okay. There's always a group structure on, okay. So, for any space, pi k of x, x naught is a group. Okay? If k is bigger than 1. Bigger than or equal to 1. It's an abelian group if k is bigger than 1. And it's always a group if k is bigger than or equal to 1. In general, the set of components pi naught of x is not a group. However, pi naught of a Lie group is a group. Okay. So was that your question?
Oh, I was asking if G is connected, so don't have this quotient.
Oh,
Then is there a group structure on the
no.
set of?
No, that's an excellent question. That's an excellent question. So, in general, absolutely no. There's this. I'm stressing that these are just the isomorphism classes of principal G bundles on Sn.
Understand.
And in general, there's no group structure on that. Okay. Right. Okay. Any other questions about the classification of G bundles on this? All right, so now I'm going to tell you a little bit about how this generalizes to classifying bundles, G bundles, on more general spaces. You might not always want to work on the n sphere, and yet you might want to know what possible bundles you can put on your space-time or your space or whatever you're working on, your phase space. Okay, so that brings us to something called the classifying space. Okay, so for any topological group, there exists a space called EG, which has two defining properties. First of all, EG is contractible. And secondly, EG has a free right G action. Now I'm going to give you examples of such an EG, a few examples later on in this lecture, and we'll construct EG for some important G's later on, like UN, and we might or might not do it for general G. In previous courses I've done it, but I think I'm going to cut it in favor of doing some other material. So unless you really want to see it, we're going to skip that. But I'll show you some examples. For the moment, just believe me, okay? Just believe me that there is such a group. Such a space. Now, assuming that it exists, we can then construct a principal G bundle simply by taking the quotient by this free right G action, and that defines the space called BG. Now, this is called the universal G bundle. And the reason for the name is that this is the Platonic principal G bundle. Every principal G bundle on any space is the pullback of this bundle by some map. Any reasonable space, paracompact, for example. So any principal G bundle on any, say, paracompact, any reasonable. Read reasonable if you don't know what paracompact means. On any reasonable space is a pullback of this one. So I call it the Platonic G bundle. What that means is, if I have a G bundle, pi over x, so given a G bundle over x, any x, there exists a map F from x into BG so that, well, BG has this over here, so that P is isomorphic to the pullback of EG. Now this map here is called a classifying map. Okay? And so therefore, and then let me remind you that if F0 is homotopic to F1, then F0 star of EG is isomorphic to F1 star of EG. And so we have the theorem, the set of isomorphism classes of principal G bundles on X, principal G bundles on X is in one-to-one correspondence with the free homotopy classes of X into this magical space BG. And we'll see in today's, maybe today, at the end of today's lecture, or maybe next time, that this is a generalization of what I just explained to you in the case where X is the n-sphere. Okay, so I'm going to give you the proof. And the proof is just pure abstract nonsense. So this really just follows by chasing through a bunch of definitions. Which means that, in a sense, you already know this. You just need to have it elucidated a little bit. Okay, so to probe this, let's begin with a very general construction. Start it over here. Supposing I have two principal G bundles. Okay, let's call them P1 projecting by pi 1 over x1, and P2 projecting by pi 2 over x2. Somebody just gives me these principal bundles. Then I define P1 times over GP2 to be P1 times P2 divided by the diagonal action of G. You see, P1 and P2 each have a free right G action. So that means that P1 times P2 has a G times G action, and I can divide by the diagonal. So, put differently, this is the equivalence, the set of equivalence classes of P1, P2, where the equivalence relation is P1.G, P2.J. Okay, now, observe that this certainly projects down to x1 times x2. Okay, and if you think about it, the fiber here is G. So this is a G bundle over x1 times x2. But, subtle point, this is not a principal G bundle. The fiber is G, but it's not a principal G bundle. Now, I think I'll let you think about why the fiber is G. Okay. Now, we can certainly furthermore project down to x1 or x2 by just projecting onto the first or second factor. And so let's call this pi 1 hat and pi 2 hat. Okay. So what do I have here? I have this thing, P1 times P2 over G, pi 1 hat down to x1, pi 2 hat down to x2. And now, you can ask what are the fibers here. So the fiber of pi 2 hat of, in other words, fiber of pi 2 hat inverse of x2 is p1, and here the fiber p pi 1 hat inverse of x1 is p2. Okay. Now, we started out, remember, with a P2 bundle, principal G bundle P2 over here, and a principal bundle P1 over here. And so we can pull these back. So we can pull this back and we get pi 2 star, pi 2 hat star of P2 over here, and pi 1 hat star of P1 over here, and I claim that these are isomorphic, and they're isomorphic to P1 times P2. And I'm going to prove that in just 1 second. So this is a principal G bundle over this quotient space here, obviously, because it's obtained by a free-run G action. Okay, so why is that pullback given later? Okay, well, what's the definition? Pi 2 hat star of P2 is, remember, it's a subset of, P1 times P2 over G, the base, times P2, such that the projection maps agree. So let me write that out. It's this set such that pi 2 of P2 is pi 2 of P2 prime. So here I'm giving you an equivalence class of a pair of points in P1 times P2 and P2 prime. So now I'm going to define a map, psi, from P2 hat star of P2 to P1 times P2 by taking this thing simply to P1 prime, P2 prime, where the P1 prime, you see what I do is I use the P2 prime here to fix the gauge. There's a gauge freedom here. This is an equivalence class by right multiplication by G. So I know that there's a unique P1 prime such that this equivalence class is of the form P1 prime, P2 prime. So using the data of P2 prime, I fix a P1 prime. So I have a well-defined map here, and you check that this is a bundle isomorphism. Okay, so complete abstract nonsense. Right, so now what we do is we're going to apply this construction. So we're going to apply this construction to which bundles? Well, remember, we're trying to show, we're trying to prove this statement right here. So we apply this construction to, over x1, we have our, x1 is x, okay? We have our bundle x that we're after. And then we have, over BG, we have EG. So this is P1, this is P2. This is x1, this is x2. Okay, so now we just complete the diagram, since we just gave a very general construction. And we have this diagram here. And now we're all set to go. If I had only left myself some room. Okay, so what do we do? I need one more remark. So as I remarked, the fiber of this map here, pi1 hat, is P2. So that means that the fiber of this map here is EG. But EG is contractible. It's one of the basic defining properties. EG is contractible. And therefore, there exists a section, call it S. So that section exists because EG is contractible. And now my classifying map, F, is going to be the composition of pi2 hat with S, up and then down. Okay. I claim that this F is the classifying map. So now let's see why that's true. Well, let's compute F star of EG. Okay, well, by definition, that's pi2 hat S star of EG. That's just the definition of this F. Now, because of the way pullback is a contravariate functor, this is S star pi2 hat star of EG. Now, I use, where did I write it? Yeah. I use this property here. Or I wrote it up at the top there. So this is isomorphic to P times EG, thought of as a principal G bundle over P cross G of EG. But it's also true, again by that property up there, that this is S star of pi1 hat star of P. Pi1 hat star is also equal to the product of P times EG. But now that's equal to pi1 hat S star of P. But S is a section. So pi1 hat S is 1. So this is P. And these are just isomorphisms here. So I proved it. F star of EG is P. That's the proof. Okay? So, abstract nonsense tells us that if you can find a space that has these properties, then you can capture all of the principal G bundles over X from the homotopy classes into this magic space BG. And that's the conclusion. Yeah, let me make a few remarks. Now, I said that these are the defining properties. But if you take a moment and think about it, of course, if EG has this property, then so does EG times EG. It's still contractible, and it still has a free right G action. So the space is not unique. So really, EG is only unique up to homotopy type. Another thing is that if G has a unitary representation, if G has a finite dimensional, unitary representation, okay, then that means that G embeds into UN, and so we can take EG to be EUN with that embedding. So really, if you construct EUN, then you've constructed a lot. You've constructed EG for any EG with a finite dimensional faithful unitary representation. And the third remark I want to make is that the cohomology groups H star of BGZ are non-trivial. Now, if I've got this classifying map, which I've unfortunately erased, so P is isomorphic to F star of EG, is a G bundle over X, and F is classifying method. Then we can, so if I have some cohomology class omega in here, then I can pull back f star of omega to a cohomology class on X. And this is what's called a characteristic class. Something we're going to be studying later. So all the Chern classes, all the Stiefel-Whitney classes, all the Pochagin classes, these are all examples of characteristic classes. Which reminds me, so I have been assuming that everybody knows de Rham cohomology. How many people have been exposed to cohomology groups more generally, like singular cohomology? Okay. So we're not going to have time in this course to systematically cover cohomology theory, but what I'm going to do for you is I'll hand out a little crib sheet, okay, with all you need to know condensed as much as I can. All right. Time for some examples. So let's look at some examples of classifying spaces. So let's start with example 1. Let's take our group to be the integers. Okay? So anybody want to volunteer a classifying space? What are we looking for? We're looking for a space which is contractible, and there's a free action of G on it. Yeah.
Real number one.
Right. So, good. So we can take EG to be R, right? R is contractible. And there's a free action of the integers on R, which is translation by the integer. Okay? And so what's BG? The circle. Okay, so that wasn't so terrible, right? I mean, you probably got scared to death by this, this general argument, but look, I mean, G is the integers. EG is just R, BG is just the circle. It's not too bad, is it? Okay, so now let's take G to be Zn. What's EG? Somebody else? Rn, yeah. Good. And what's BG?
Yeah, SMS is less
The torus. N-dimensional torus. Thank you very much. Okay. Okay, that was easy. Good. So, let's look at example 2. Let's take G to be a really simple group. Z2. Doesn't get any simpler than that. Okay, now we're looking for EG. So you want a contractible space where Z2 is acting freely.
What is acting freely?
No fixed points.
I see. For any group element, it will,
Any group,
it
yeah.
will be identity to such a
No element is fixed by a non-trivial element of the group. Put differently, if I take any group element which is not the identity,
Then
it always moves elements. It has no fixed points. Very, very crucial property. So in this case, there's only one non-trivial element. Right. And so that guy is not allowed to have any fixed points. Okay, so how do you want Z2 to act? Think of us, what space does Z2 act on? Good. Okay, S2. So Z2 acts by the antipodal point, I assume is what you have in mind, by the antipodal map. There are other Z2 actions, but let's say the antipodal map. Why won't this do for EG?
circle along the hemisphere is fixed.
No. It's this is a free action. not contractible, right? No good. Okay, try again. RP2. How does Z2 act on RP2? Pardon?
Oh,
No, it doesn't. That's the quotient.
Yeah.
Okay, now one more.
So we have to.
Come on, it's just one group element. It squares to 1. I'm asking for just one group element, squares to 1. Okay, it acts on a space that's contractible and acts freely.
So contractible means simply connected.
No, contractible means there's a deformation retract, homotopy. There's a homotopy contracting it to a point.
So it can be not a non-connected space.
No, it's got to be connected. If it's contractible, it all has to, it's at one point.
Mobius strip.
Mobius strip.
How is that contract?
How is that contractible? Not too contractible.
C star.
C star. Not contractible. How about Rn? Doesn't Z2 act on Rn by reflection?
Yeah, just reflection of the origin.
But there's a fixed
Around the
point.
origin, but it has a fixed point. Rn is contractible, okay? But it has a fixed point. Okay, doesn't look so simple, does it? But you were on the right track when you said Z2. I mean, after all, we could have replaced that by Sn. Oh, when you said S2. You could have replaced that by Sn. It's still true that the antipodal map on Sn is a freely acting map. But of course, Sn is not contractible. But wait a second, what were the homotopy groups of Sn? So pi j of Sn, at least the ones in low dimension. Those were 0 for j less than n, right? Now, if your homotopy groups are all 0, then you've got a good bet that you've got a contractible space. Now, they're not all 0. They're 0 up to n. Does that suggest anything? Take n to infinity. Why not? So, how about EG equals S infinity? What is S infinity? It's equal to the unit sphere in the real Hilbert space L2 of R. Well, we certainly have a fixed point free action. We could still define the antipodal map, x goes to minus x, on the unit sphere in Hilbert space. Okay, so S infinity is the set of x1, x2, such that the sum of xi squared is 1, and think of that as sitting in L2 R, the real Hilbert space, L2 R. Okay? I claim this is contractible. So the finite dimensional spheres are most definitely not contractible. We talked about the higher homotopy groups that are interesting, and so on. But the infinite sphere is contractible. Now, why should that be true? Well, let's consider the Hilbert hotel map. Okay? The Hilbert hotel map is this map. And I claim that we look at Tx plus 1 minus T S of x, okay, that this never vanishes for x in S infinity 0 less than or equal to T less than or equal to 1. Okay, so I'll let you show that. You take the norm squared, you do a few estimates, some hints are in the notes. Okay. So therefore, I can divide by this and make it norm 1. And so that is an explicit homotopy between the identity map at t equals 1, right, and the Hilbert Hotel map at t equals 0. So what is that doing? What is the Hilbert Hotel map doing? It's mapping all of the sphere into the hemisphere, right, by putting the first coordinate to 0. So the Hilbert Hotel map maps the whole sphere into the hemisphere. But now you see I'm home free, because of course I can contract the hemisphere back to a point. On the other hand, the Hilbert Hotel map is homotopic to the identity map. So I just did it for you. I contracted the infinite dimensional sphere to a point. Well, that's REG. Okay, so EZ2 is S infinity. So BZ2 is what? Well, let's remember that this is the limit of Sn, and what is the principal Z2 bundle over S of Sn? It's over Rpn, as when Z2 is the antipodal map. And so BZ2 is Rp infinity. So what we're saying is that if you want to classify double covers, the classification of double covers of X is by homotopy classes of X into Rp infinity. Now, of course, if X is n-dimensional, these homotopy classes are only going to see Rp infinity up to Rpn for some finite n. So you don't have to go to Rp infinity all the way. But this is a true statement for an arbitrary X. Now, by the same token, we looked at a number of other fibrations over spheres, and we can use this contractibility of the infinite dimensional sphere also to show that BU1 is Cp infinity and BSU2 is HP infinity by the other fibrations that we had before. Okay? Remember that we had U1 going into S2n plus 1 over Cpn, right? So again, you can take the infinite limit here, the U1x freely on this, and so BU1 is Cp infinity. Okay, now we will show in a few lectures that BUN is the limit as n goes to infinity of the Grassmannian of n planes in capital N dimensional space. A few other examples. Now, I haven't officially introduced gauge theory yet, but well, you'll have some sense of gauge theory. So one example you might have is that if X is now a space-time, and we have a compact gauge group, then we have the group of gauge transformations, curly G, which if we have a trivial bundle on space-time, is just the maps from X into G, and we could fix a base point, make G of X not equal to 1. And then E of this curly G is the space of all gauge potentials. And BG, for the group of all gauge transformations, is equal to the space of gauge equivalent connections. In other words, physical connections. We're also going to talk about Riemann surfaces a little later, which gives another example of EG and BG. Now, if you're not comfortable with this S infinity stuff, you can make this rigorous with something called the inductive limit. Okay, and it's a little technical and dry, so I'm not going to bore you to tears by going through it, and it's in the notes. Okay, so there's a rigorous way of making sense of the topology of what I mean by S infinity, R infinity. So, for example, in R infinity, an open set in R infinity is open if it's open in Rn for all n, where I embed R in R2, in R3, and so on by taking x to x comma 0, and I take x1, x2 to x1, x2, 0, and so forth. Okay. So there's a well-defined way of making this, taking these limits. Yes, one more thing to finish this chapter. So I want to stress that what I'm doing here is talking about isomorphism classes of bundles. Pan was asking a very good question before. So, does everybody know what a groupoid is? No? Okay, so does everybody remember what a category is? Yeah, okay. So you remember a category, we have objects and we have arrows, and every object at least has the identity arrow to itself, and the composition of the arrows is associative. So a morphism in a category, f from object x0 to x1, is invertible if there exists a morphism G from x1 to x0 such that f composed with G is equal to the identity morphism on x1, and G composed with f is equal to the identity morphism on x0. I think we've been through that before. Now a group is a category with one object, and all morphisms are invertible. Okay, there's a picture here we might develop more later on. It's a very, very useful picture. So there's your one object, and now group elements are like little loops from that object to itself. And whenever I have two little loops like that, I have another loop, which is the composition of those morphisms, and that's the group multiplication. And then because all morphisms are invertible, group elements are invertible, and then we also have the associativity law in the morphisms, so those are the axioms of a group. So a group is just a category, all of whose morphisms are invertible. So, definition. A groupoid is a category, all of whose morphisms are invertible. So the only thing I've done here is I've allowed the possibility that there's more than one object. So I have an object here, I have an object here, and here. Now there are morphisms. Every time I draw a morphism, there has to be an inverse morphism. There's a morphism, there has to be an inverse morphism, and of course there's always the identity morphism. So that's the picture of a groupoid. Now, bundles on X, or principal G bundles, form a groupoid. Because if I have two of them, I have a notion of a bundle isomorphism, which we've defined before. Now, when you have a groupoid, you can talk about the isomorphism classes. Of objects in a groupoid. And they should be distinguished from the objects themselves because of the existence of automorphisms. So for a bundle, a principal bundle, an automorphism of a principal bundle is a bundle map from P to itself. In other words, it commutes with this G action and projects that to X. Okay. So what we've been classifying are isomorphism classes. But the fact that there are automorphisms of the object can be very important. It's like having a fixed point. Okay? And there's always this data of that fixed, the group elements that preserve that fixed point, which can be very important in lots of considerations. So I'll talk more about that later. So, yeah, let me give an example of these automorphisms. So we showed that the principal G bundles on Sn is pi n minus 1 of G. Now, what are the automorphisms? And I'm saying that the G bundles form a groupoid. And what is the automorphism group of some principal G bundle over Sn? Anybody know? There's a group of automorphisms of this. So think of the trivial bundle. Okay? Supposing I just have the trivial bundle. What would the automorphisms look like? Okay, well, look. The trivial bundle is Sn times G. We have to have some map here, Sn times G. It has to project to Sn. It has to be a bundle morphism. So that means it has to look like multiplication on the right by some map. So it has to be multiplying on the right by theta G goes to theta G times some H of theta. Okay. And that H, therefore, defines a homotopy class in pi n of G. Okay. So if I look at these automorphisms up to continuous deformation, then the group of these things is the homotopy group pi n of G. So for example, if I look at principal SU2 bundles on S3, that's going to be pi 2 of SU2. SU2 is the 3 sphere, so that's 0. So there are no non-trivial principal SU2 bundles on S3, right? We've proven that today. But, so that means that if you have any principal SU2 bundle on S3, it's equivalent to S3 times SU2. But there can be different trivializations, and different trivializations, okay, will differ. Different trivializations will differ by a map from S3 to SU2, okay, which has its own homotopy class. Pi 3 of SU2 is Z. So there's a whole integer's worth of different trivializations. Okay. Well, let me just get us started on the next chapter, and of course we won't get very far, but let's just see where we're going. So the next chapter is about, well, it's going to be about a few things. It's going to be about covering spaces, about gauge theories with a discrete gauge group, and about the stable homotopy groups of the compact Lie groups. And the main technical tool will be what's called the long exact sequence of homotopy groups associated to a fibration. Now I'll say what a fibration is more precisely next time. It's a slight generalization of a fiber bundle. Let me just tell you the main theorem we're going to prove next time. The main technical theorem we're going to prove. Which is this. Supposing that I have a fibration, or a fiber bundle, but more generally a fibration, F, it's not principal bundle anymore, it's just any fibration. So I have F goes into the total space over the base space. And I'll use P here, because I don't want to confuse it with the pi's from homotopy groups. And in fact, well, those technical things I'll prove next time. So there's some inclusion of the fiber into the total space, and then the projection to the base. So here's the picture. So we have our F, we're including it into here, and then we're projecting it down to the base. So what I claim is that the homotopy groups of F and E and B are all related. Okay? And the relation is going to look like this. There's going to be a map of pi sub k into pi k of E into pi k of B. So that, of course, is going to be true for every k. And so it's true for k plus 1. And it's true for k minus 1. Now, the real mileage we get out of this is that it turns out there's a map called a connecting homomorphism. It goes like that. So you have what's called a long exact sequence. And this is an exact sequence, which means that at every stage of the game, the image of this map is the kernel of that map. And so we're going to prove that